Hello, Team Shenandoah. Welcome back. Today we're doing two lessons at one time, compound probability and fundamental counting principle. We have a lot of vocab words in this section that are going to be new to you. So make sure you review and read over these vocab words and can recognize them and know what they are when we're finished. So far we've talked about simple probability, which means one event. Now we've got a compound event, which consists of two or more simple events. Two or more simple events. The sample space is all of the possible outcomes in a probability experiment. All of the possible outcomes. And we're going to be showing those in different ways. All of the possible outcomes. I like to think that the sample space shows a sample of each outcome. So again, this will be just showing us all the different things that could happen. A tree diagram is one way to show a sample space. The other way is really a list. Instead of visually making a tree diagram, you can also use the fundamental counting principle and use multiplication to find the number of outcomes in a sample space. So the fundamental counting principle isn't showing us anything, it's just going to be a way to tell us the number of possible outcomes. And it's really pretty simple, it's just multiplication. So we're going to see all these things in the notes now. So notice the directions. The spinner at the right is spun twice. It's a simple spinner, only 3 options. But what's everything going to look like now that this is compound probability and 2 things or more are happening? So number 1, draw a tree diagram to show the sample space of the situation. So one of the ways that we can show what's happening. So I'm going to write our first spin. What are all the possible things that could happen on our first spin? You could spin an A, you could spin a B, or you could spin a C. So 3 different things could happen. On your second spin, obviously all the same things could happen. So your first spin could have been an A. Your second spin could have been an A, a B, or a C. If your first spin was a B, you still could have gotten an A, B, or a C for your second spin. And the same for C. So we got to break it down. Our first spin, what are all the things that could happen? And on our second spin, what are all the things that could have happened? So I'm going to add to this a little bit. This is showing a tree diagram. But if we wanted to list this a different way and just saying what the sample space is, it's basically writing what we see here. You could say first you get an A, second you get an A. That would be one outcome. First you could get an A, next you could get a B. I'm just going to list them. First you can get an A, then you get a C. And we've got 6 more possible outcomes. We could have a B, then an A, a BB, a BC. We could have gotten a CA, a CB, or a CC. All of the possible things that could have happened with 2 spins. This kind of helps us with the next question, which is why I wrote it a different way. What's the probability of getting at least one A? So if we look at all the possible outcomes here, there's 9 of them total. How many of them have at least one A? We've got AA, AB, AC, BA, and CA. That is 5 out of the possible 9. That's going to be our answer. And again, this is a compound event because 2 things happened. Alright, so what now for number 3 is the fundamental counting principle, and you'll see how these answers are related. Use this to find the number of outcomes in the sample space. Well, we already know, because we did some work, that there's 9 possible outcomes. This is simply some multiplication. In your first event, the first spin, there were 3 possible outcomes, getting A, B, or C, so I write the number 3. I'm going to multiply that by how many things could happen in the second event. 1, 2, or 3. A, B, or C again. 3 times 3 is 9. As we already knew, again, there were 9 possible outcomes that could have happened. So this is exactly what fundamental counting principle looks like. It's just multiplication. And every time I write it, I like to write a line, and I like to describe what's happening. On to the back side. Some more. For each situation, use the fundamental counting principle to find the number of outcomes, then make a tree diagram to show the sample space. So in the first situation, choosing a hamburger or a hot dog and potato salad or fruit or a salad. So we're going on a picnic. It looks like these are our main courses. And then we get to pick one of these sides. Okay, so first, the fundamental counting principle. I have 2 possible main courses, I'll just describe it that way, times how many sides? Times 3 sides, for a total of 6 possible combinations or outcomes of all of these. And now we'll make a tree diagram to see what they all are. And I'm going to abbreviate. You can always abbreviate as long as the person or me knows exactly what the abbreviation stands for. So our main course could be a hamburger or ham or a dog, a hot dog, main course. Then you could pick either potato salad or fruit, FR, or regular salad. Same thing for your hot dog, potato salad, fruit, or regular salad. You'll notice that whenever you draw a tree diagram, all of the options you have down here should be the same as the number of outcomes you could find for the fundamental counting principle. So 6 outcomes. This is like the tree trunk, and these are the branches at the end. So we've got 6 branches that come out. I could also just list all of these, but I don't need to do that right now. So our tree diagram shows all the outcomes. Moving on, number 2, choosing between the numbers 1 or 2 and the colors mauve, which is a type of purple, violet, green, or gold. Who made up these crazy questions? I don't know. So first we have fundamental counting principle. We have 2 events happening. Event number 1 is picking a number, and event number 2 is picking a color. I had 2 numbers, so I just put 2 there, and I have 4 different colors. So that means I'm going to have 8 total outcomes or combinations of these. To make a tree diagram, first I'm starting with the first event, picking a number, 1 or 2. And I have 4 different colors I could pick after that. Mauve, violet, GR for green, GO for gold. And the same for number 2. Again, I have a total of 8 outcomes or combinations of things that could happen, picking a color and a number. For number 3, let's talk about money. Toss a quarter, a dime, and a nickel. What is the probability of getting 3 tails? So fundamental counting principle again. I have 3 different events happening. So this time 3 lines. My first event is tossing the quarter. Q for quarter. Second event, tossing a dime. Third event, tossing a nickel. Well, every time you toss a coin, there's 2 possible outcomes, heads or tails. That's true for a quarter. The same is true for a dime. The same is true for a nickel. 2 times 2 times 2 is 8 possible outcomes. Now let's draw this. Now this is the first time we've seen 3 events happening. So our branches are going to be longer. First event. So give yourself some space here. First event was the quarter. So 2 options again. You could have flipped a head, H for head, or T for tails. The second event was flipping a dime. So I could get, again, heads or tails. And our third event, flipping the nickel. Heads, tails, heads, tails, heads, tails, heads, tails. Gets a little repetitive, but we have 3 layers or 3 different events, so make sure there's 3 different layers here to our tree. Again, at the bottom, if we count all these up, heads, tails, heads, tails, heads, tails, heads, tails, there's 8 outcomes, just like we found for the fundamental counting principle. Let's write this one out a different way, though. So sometimes a tree diagram is easier to see. Probably in this case it will be. But let's see how you write out all these options, because it can help us sometimes. Sometimes it's, and you may be asked to write out the sample space, or you may be asked to write a tree diagram. So be able to do both. So if I follow the pathway down these branches, I want to write every option of what happens. So first I have heads, heads, heads. Go down the next branch, heads, heads, tails. Third one, heads, tails, heads. and then heads, tails, tails. Going on to our fifth branch, tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. Kind of makes a pattern. So again, this is another way to show the sample space. All of the possible outcomes written out. And a tree diagram is also a way to show a sample space. Okay, now some fun ones. If I were you, I would pause for a moment to get your phone or a calculator, because we're going to do some calculations here, and you'll want to find out the answers yourself without me telling you all of them, because it'll be more fun for you. So I'll pause for a moment also while you get your calculator. All right, welcome back. So let's talk about some real life type of things here. Number one, in the game Bunko, maybe some of your moms play that, you roll 3 number cubes or dice at a time. What's the probability of rolling a 3, a 3, and a 3? So a 3 on each of your 3 dice. We have 3 events happening. And by the way, our instructions were we're using the fundamental counting principle to find the total number of outcomes. So I have 3 events. I can just call them event number 1, event number 2, dice number 1, dice number 2, dice number 3. When you're rolling a dice, of course, there are 6 possible options of what you could get. 1, 2, 3, 4, 5, or 6. So, number of outcomes, 6. And for every dice, it's the same thing. So how many possible outcomes are there when you roll 3 dice at a time? Multiply this. 6 times 6 times 6. Feel free to pause if you don't want to hear the answer. But that is 216 outcomes. So that doesn't necessarily answer my question. If I want to know what are the actual chances or probability of me getting exactly what I want, 3 3s, then that would be 1 out of the possible 216 outcomes. Pretty small number. Go ahead and use your calculator to find out what is that as a decimal and what is that as a percent. So remember, you divide. So 1 divided by 216. You get a very small number, 0.0046, and I'll just leave it there as a percent. We'll move the decimal point over twice to the right. So this would be 0.46%. So about 0.5% chance of that happening. If you know anyone who plays Bunko, ask them. Ask them how often they get Bunkos. Number 2, let's say you go to Baskin Robbins. Choosing from 35 flavors of ice cream, 1, 2, or 3 scoops, and do you want a sugar or a waffle cone? How many different outcomes or combinations are there? Now, one detail here that we're going to assume. We're going to assume that you can only pick one flavor, even though there are 35 possible ones to choose from. So we've got 3 events. The first one is flavor. The next one is how many scoops. And the next one is what type of cone. We have 35 possible flavors to choose from. We could choose 1, 2, or 3 scoops. And we have 2 different types of cones. Go ahead and multiply those together. Maybe you can do this mentally. 35 times 2. And then multiply that by 3. 210 possible combinations or outcomes. But really, there would be more. If you picked 3 scoops and picked 3 different flavors, there would be a lot more. How about license plates? License plate that has 3 numbers that can range from 0 to 9 and 4 letters in which each number and a letter may be used more than once. So in California, this is what our license plates look like. How many events are happening here? 3 numbers and 4 letters. That's 7 events. This is going to be a really big number. First 3 events, number, number, number. Then letter, letter, letter. How many numbers are there from 0 to 9? It's not 9, but it's 10. And each number can repeat. So we've got 10 numbers times 10 numbers times 10 numbers. And there are 26 letters in the alphabet. And these can be used, again, more than once. Keep in mind, as you multiply out this ginormous number, that this isn't even reality, because in California we have all these symbols, hands and hearts and things like that you can put on your license plate. You can also have blank spaces.